Welcome to the Handbook of Statistics, a series in which I try to vulgarize and animate statistical concepts. In this video, we're going to talk about neural networks and understand how they work. So let us begin with the beginning and represent our data. We have a set of training points, X values and Y labels. The goal of our neural network will be to predict the Y label when given an X input. As you can see, I didn't choose a random linear function, but a complex nonlinear one, as you can see with the sinus term. The more complex, the more difficult it is to approximate the function. In the next animation, we will see the training sequence of a neural network. Basically, we will see how it gets better over each iteration. As you can see on the screen, the blue dots represent our training data points, and the red line represents our predictions. On the top left of your screen, you can see MSE. This represents our loss function. A loss function is basically a measure of how far we are to the actual values. To do that, we have split the set of training points into a set of training points and a set of testing points. After 1000 iterations, as you can see, we have successfully modeled the function. But how does it work really? Let's dive into the math of neural networks. A neural network is nothing but a collection of neurons. Each neuron is represented as a circle on the screen. The blue circles represent our inputs, the red circles represent the neurons of the hidden layers, and all of them converges towards the green circle, which represent our outputs. The white line that you see represent the passage of information from one neuron to another. With each training iteration, the neural network optimizes the weights and biases that connect one neuron to another. Ultimately, when it has converged, the output remains the same. So now you get the idea of what a neural network is, but let's understand the math behind it, because it can get a bit monstrous, let's be honest. But if you break down the terms, it's actually very simple. We have seen that the output neuron compiles all the information from previous connected neurons to give an answer, a prediction. This is our Y value represented on the screen. A neuron is a linear function of the previous connected neurons plus a bias. These weights and biases are basically updated with each iteration through a method called gradient descent. Basically, if after a change the change is positive and we are getting more accurate, it continues to go that direction. So now we know what a neuron is and how it is represented. It's just the weighted sum plus a bias of the previous connected neurons. Iteratively, we get this kind of function. The f that you may have seen is just an activation function that introduces nonlinearity. Otherwise, we have a polynomial expression which makes it difficult to approximate non-linear functions such as the one that we have seen previously. The more complex the function, the more hidden layers we need and the more neurons we need to capture its complexity. At the end of the day, creating a decent neural network requires two things: sufficient training data, otherwise we cannot train and optimize our weights and biases. Next, we need a good model. Otherwise, we cannot catch the complexity of a function with just a linear function and an activation function. The more hidden layers, the more complex and the more potential it has, but the more computationally greedy it becomes. In the previous simulation, I iterated many times to find a good architecture because I didn't want to go through a lot of iterations. There were many hidden layers, 2 to be exact, and many neurons, 50. It allows us to capture the complexity of the sinus term of the function. If I were to predict value on unseen data, it would perform likely very well. But let's do an experiment. Let's put much less neurons and do the very same simulation. Starting from the first iteration, you can see that the mean square error, which is our loss function, it is already very high. As the number of iterations grow, the mean square error decreases, but as you can see, it has difficulty to capture those complex terms. I limited my simulations to 1000 iterations and maybe it would converge, but my point is if your architecture is much simpler, it will take much more iterations to converge. But of course, the architecture of the layers is not the only thing that matters. For example, we have the bias and variance trade-off, the number of iteration, and choosing the right activation functions. Ultimately, you will have to tweak your models as much as needed to find the perfect match. The criteria can be the loss function, but you don't want to overfit on data to perform well on unseen data. This is the bias and variance trade-off. You want to minimize both of them, but if you minimize the bias, the variance will increase on unseen data. If you are limited in computation resources, for example, if you don't have access to a big supercomputer, and if you have time limitations, you have to choose a good architecture, one that is not too complicated, to make sure that your model converges. But if done correctly, and you tweak your models and you give yourself the time to investigate and read research about it, you will achieve your goals without a doubt. Neural networks are not that complicated. Thanks again for watching, and please subscribe and like this video if you enjoyed it.